Welcome back, ladies and gentlemen. We're going to be talking about velocity time graphs in this particular one. Everything up until now, of course, has been about position, distance, displacement, stuff like that. But velocity time graphs, they're a little bit more complicated, or at least a little less familiar. Since you guys have been working in middle school on graphs, we've spent a lot of time showing you graphs. We've asked you guys to graph things. And generally speaking, we did a lot of position graphs when you guys were growing up because, they're fairly straightforward. You can see these things pretty easily. There's the calculator, and then I move the calculator, and now it's there. That's pretty straightforward. Velocity graphs rely on things that are a little bit more esoteric. They're not as bad as acceleration, which we're not going to do, but they are a little bit worse. On the plus side, though, they are very, very useful. Velocity graphs can be exceptionally beneficial. So, with that in mind, let's erase things here and get to it. Now, the big thing that's going to cause people trouble when it comes to velocity graphs is that you guys are going to want to default to position graph ideas. Things you already know. You're going to turn a new problem into an old problem, which my grade 11 students will be able to tell you is something that I ask them to do all the time. But we got to be careful here because similar looking things can mean very different things. So on page 44 is where this stuff is. And so the first thing is that the graph is going to show velocity over time. Okay? And of course, this involves a vector. Now the units here, velocity is generally going to be in meters per second and time is going to be in seconds, but they could be in kilometers per hour and hours. It just depends on the situation. And the symbol that we usually use for this is going to be, got to write the whole symbol. It's going to be VT. So that's how I would usually refer to it in just a symbol. I would say this is a VT graph, okay? All right, so terms. There are 4 terms here. There is the, of course, velocity, which we get from the y-axis. There is the time, which we get from the x-axis. So we read those right off there just like normal. There is the acceleration, which we get from the slope. And everything we've talked about in terms of graphs, this has pretty much been the way it is. But there's one last thing, because as I mentioned, velocity graphs are very, very powerful. They can do a lot, and this is the last thing that they can do. A velocity graph can give you displacement. And so there's 4 instead of 3. And that 4th is found from the area. You know, of course, what area is. You've calculated area before. You've dealt with it in the past. But how in the world can I use area to get displacement from a graph, no less? Now, we're going to do an example to show you guys exactly how to do that in just a second. But first, let's fill in the shapes. So shapes, okay, the shapes, there's actually only 2 shapes that we really are concerned with. Okay, so there are 3 lines in your graph, but we'll mention them, okay? So the first one, of course, as we've seen before, is a flat line. A flat or a dead line, as my former students have once mentioned, means that you've got a constant velocity. Now this is different from a position time graph. In a position time graph or a distance time graph, a flat line did not mean constant. In a position time graph, a flat line meant not moving. So this is the big difference. If, let's say I use colors here, right? If I had a position time graph, which I'll just do really quick, and I had a velocity time graph, also very quick, and these are just graph sketches. So if I did the position time graph in green, I get this, which means v equals 0. This means v equals a specific number. And that's it. Those are the only 2 differences. Now, Will that be confusing? Yeah, because you just spent a bunch of time, presumably, working really hard, making sure you understood exactly how this all worked, and now you're looking at it going, but it's different. And people always hate it when things are just slightly different than what they already know. Speaking of slightly different, a sloped line. This means changing velocity. Or put another way, means there's an acceleration. And then the last one, a curved line. What's a curved line mean? Well, curved line means changing acceleration. There's more than one acceleration value. And because there's more than one acceleration value, it gets things really messy, really complicated. But here's the wonderful thing. See that last one? Yeah, we're not doing that. Heck, I don't even do that one with grade 11s. I don't even think the grade 12s do that one. We wait to university to give you guys that. It happens all the time, like 24/7, whenever you guys are doing anything, you don't have the same acceleration, right? Sometimes you get tired, you go a little slower. Sometimes you got more energy, you go faster. You leave class a lot faster than you show up to class, is what I'm saying. So these are the only two that we're going to see in our graphs, okay? Flat lines and sloped lines. So on the plus side, already, this is going to be a simpler kind of problem. But there is this new thing for us to deal with, displacement from the area. And we got to see how in the world do we do that, okay? So there's an example on your page in front of you, and we're going to work through it together, and I'm going to show you guys exactly how to do this. So if we draw a quick sketch of your example, it says here that it's from 0 to 25 seconds. Okay, so let's get lots of space here. So we make a nice big graph. Okay, so from 0 here, and then we're going to do, let's see, 5, 10, 15, 20, 25. Okay, and then the velocities are from 0 up to 20. Okay, so 0, put 20 up here at the top. That means 10 goes in the middle. There's a 15 and then a 5. You'll notice I didn't do that with the 25. That's because 25 doesn't cut in half as easily. It's one of the reasons why it's a little bit of a pain to work with. I probably would have worked with 30 instead, but yeah, you know what? We'll just go with this. Then this particular graph here goes 5 up to 20 here. Okay, and there's a dot there at the start. And then 15 is also 20, so up to there. And then the last one, 25, goes down to 10, which is right there. I went and got the ruler. It's attached with magnets to make this a little bit easier. But, you know, drawing lines, always a challenge. There you go. So there is our graph. And now, if I were to ask you guys for, say, the velocity, right? So if we were looking at this graph and I said, okay, guys, what's the velocity at 10 seconds? Well, to get velocity, it tells us in our list of terms, we would read off of the y-axis. So I would find 10 seconds, which is right here. And I would read up until I see that spot on the graph, and then I would read over. So this is 20. So the velocity at 10 seconds is 20. Okay, pretty straightforward. If I asked you at what time was the object moving at 5 meters per second, well, 5 meters per second is the velocity, so then there it is, okay, 5 meters per second. I would look across until I found the graph, okay, there it is, and then I would read down and go, oh, okay, at 5 seconds, it was moving at 5 meters per second. So that is how I get the time, right, because I would just read it off the x-axis. Now, I could ask you guys for the slope. I could ask you for the acceleration, right? We know how to calculate that. We've done that a whole bunch over the last lesson. We would take 2 points from the start and from the end, and we would compare them. So in this case here, for example, we're just going to do it, right? This isn't necessarily something that you already know how to do this, but we can still talk about how to do it. And what we see is that this one here is going to be at point 5, 20, and that's the second point. And down here, we're at 0, 0, and that's the first point. So if I were to find the slope, just like so, it's going to be change in y over change in x. So y2 is 20 minus 0 over 5 minus 0. So in this case, the slope would be 4 meters per second squared. And positive, because it's positive slope. This one over here, of course, is a negative slope, as we can clearly see because it points down. Okay, so there we go. We have our basic information. So now what do? Well, there's this whole area thing, right? We haven't done that before. How do I do it? What do I do to calculate the area? Well, the first thing is we need to find some areas. Like area. This is a graph, it's a line. How do I have an area? Well, the way we usually do it, I'll do it in green, is that we talk about the full sentence is not just find the area. The full sentence is find the area under the curve. Now, a curve is just a fancy math way of saying the line that you use to make a graph. This one isn't really very curvy, it's more straight, but that's fine. Under the curve. In this case, it means the area from the line down to the x-axis. So if I were to shade it in, I'm asking you, what is that area? That's what I want to find. Okay, well, a very fancy and clever person by the name of Sir Isaac Newton figured out how to do that using a technique called calculus. But we're not Newton, and you guys don't all know calculus yet. So we've got to find another way to do this, and there is, thankfully. You see, one of the things is that when you're confronted with a new big problem, break it into a bunch of smaller problems. So this whole thing has an area. I don't want to do the whole thing at once. I want to do something simple, okay? And what is simple? Well, there is something very simple that we can do here. I put the line, and I go straight down, and I go straight down. What did that do for me? Well, we do these with different kind of markings just to make it easier to see. Got one shape here, and I've got another shape there, and then I got a third shape at the end. What are those shapes? I hope you guys know. If not, well, okay. You're about to learn. It's a square. Rectangle. That's a triangle. And this one here is a weird shape called a trapezoid, but to make our life a little easier, what we can do is break it into two shapes. A square and a triangle. Well, I know how to deal with squares and triangles. I know how to calculate those. There's nothing fancy about that. Squares, triangles, no big deal. Let's try some. For ease of use, I'm going to name or number each of the sections. Okay, so we'll get out the red here. I'm going to say this one here is going to be section 1. This is going to be section 2. I'm going to make this one here 3A and 3B because they're going to be connected. Okay, so let's start with 2. I know it's weird to start with 2, but 2 is easy, right? Because I'm talking about area, right? Area of a square. If I wanted to write that with more of a math form, area of a square. What is the area of a square? Do we remember the formula? Do we remember how to calculate the area of a square? Maybe. You could look it up, or you could just wait and I'll tell it to you. The area of a square is going to be the base times the height, or maybe the length times the width, something like that. Well, here's my base. From there to there. Right? That's a base. And here's my height. From there to there. So, the base, well, how big is that? 5 to 15. Well, that's just 10, right? So it's going to be 10 times, what's the height? Oh, it's from 0 to 20, so that's going to be 10 times 20. So the area of that square is 200 meters. Wait, why is it meters? Why is it meters? Well, let's take a look. 10, that's seconds. Okay, so seconds. 20. Well, 20, that's the velocity. That's going up and down. Well, the velocity is in meters per seconds. Well, by algebra, this s cancels this s, and you're just left with m left over. So we get meters. Well, it's very convenient that the graph is designed that way. That way we get this number that we really know how to use already. It's almost like they did that on purpose. So what is this telling us? This is telling us that if you were to travel for 10 seconds at 20 meters per second, you would go 200 meters. That's what this means. The area underneath, or between the axis and between the x-axis and the graph, the area in there tells you your velocity. Tells you your displacement. Tells you how much ground you cover. Now, why is this useful for us? Well, remember, people are good at pictures, but they're not great at numbers, right? So take a look at this graph again. 1, 2, of those two shapes, which one is bigger? Right? Which shape has more green colored in? I think you can all tell. It's number 2. So guess where I covered the most ground? 1 or 2? It's 2. During section 2, I covered the most ground. And we'll see that because we're going to do the calculation for 1 right now. Let's do it. 1. Okay, so 1, area of a triangle is equal to base times height over 2. You really should know that. So the base here is from 0 to 5. So this is going to be 5 times the height is still 20. But I'm going to divide it by 2 because it's a triangle, right? A triangle is half the square. So there's like this whole section here that's missing right now. So 5 times 20, well, let's see, 5 times 2 is going to be 10. And then I add a 0, so it's 100. Divided by 2, that's going to be 50. So this is going to be 50 meters. Well, 50 is smaller than 200, and that makes sense because this section of the graph is bigger than this one. So in 1, I don't travel as far, and in 2, I travel quite a distance. So this is all that they mean when they say that you can get the displacement from a graph by checking its area. You just break the thing into shapes, triangles and squares, and then you calculate, and then that's it. We can do the last part, 3. We'll do it down here. 3 has both a square and a triangle, so we've just got to be careful about how we do this. So the area of 3 is going to equal to the area of the square plus the area of a triangle. See? There's 2 parts here, A and B, so we just put them together. So B, well, let's do that one. So it's going to be base times height. Well, the base here is from 15 to 25, so I'm going to take 25, I'm going to subtract 15, I'm going to get 10. So we get 10 times, well, the height of the square how big is it? We've got to be careful about that. So we check here, and the height of the square should be at about 10, right? Because it doesn't go all the way to the top. The square stops about here. Now, my drawing up here on the board is a little bit rough, but if you look in your notes, it's 10. So that means that this is going to be 10 times 10. The triangle on top is still 10 big, but it's not 20 tall. It's only from here, 10 up to 20. So it's only 10 tall. And then, of course, I divide it by 2. So what happens when I put all this together? Well, this is going to be 100, and this is going to be 50. So overall, section 3 is 150 meters. So, if I were to ask you in a question, how far do you travel during the whole trip? You would calculate each area, just like we did here, and then you just add them up. So the total displacement here would be 200 plus 50 plus 150. And we would get, 0 carry the 1, 400 meters in total. And that's it. That's all you have to do. It's all stuff you already know, you've already seen, and you've already done. It's just you got to be careful about, what is the question actually asking you? And that's always the hard part with this stuff, is that people end up going like, what is the question actually asking me? And they just start throwing numbers into formulas and hoping that the math makes it all go away somehow. If you pay attention and you're careful, you'll be okay. It's just about making sure that you don't get yourself lost. So, with that in mind, okay, you guys now have the ability to try pages 45, 46, 47, 48, 49, and 50. Okay? Take your time on these, ask questions. There will be a few that'll probably throw people, right? That first graph was all a positive graph, but the very next page has a graph that looks something like this. I'll just very quickly sketch it here. Very, very, very simple one, okay? So it looks something kind of like this. It's a very standard looking graph. These type of graphs come up all the time. This part here, at the start, well, that's pretty similar to the one we already had there. But the second part, not so much. That part's below the axis. And what usually throws people is that they'll be like, okay, area under the curve. I know how to do that. I'll just draw an area that goes here down all the way forever till I run out of paper. And I'll find out what this area is. Look at that. That'll be great, right? Because that's under the curve. And look, it goes so far. So it'll be a nice big number, and it'll be really impressive looking. Yeah, that's not how you do it. You can tell, because I did it to what's called absurdity, right? I took it all the way to the bottom of the board. When you're doing the area under a curve, you always go from the graph to the x-axis. So here, we went with the graph down, but when we're underneath the axis, we would go from the graph up. So it becomes this area here. Okay? Not this weird little thing that I drew that went all the way to the bottom of the board. No. It's the area between the graph and the axis. Okay? All right, guys. So that's kind of the information that you need to be able to give these a try. You've got answers. They should be located, let's see, 47 has answers located on the bottom of the page, so does 48, and not 49 or 50. Those ones are all located in the booklet, if I remember properly here. I'm taking a look. Yes, the answers are located in the booklet on page 45, 46, and 47, and 48. Okay, so you guys will be able to check your work in the answer key booklet, and you guys can, of course, ask questions just like normal. Hopefully things are going pretty well. Hopefully everyone is enjoying some time outside. It's finally a little bit warmer. It is no longer 15 degrees in this room, so that's nice. And I will talk to you guys next time.